Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're examining computer vision breakthroughs, 17 revolutionary papers that are reshaping how machines see our world. On November 26, 2025, researchers published groundbreaking work spanning from three-dimensional understanding to real-time generation, from medical AI to mobile deployment. This comprehensive analysis reveals discoveries that could fundamentally transform visual artificial intelligence. Picture this: on a single day in November 2025, 17 groundbreaking papers emerged that could change everything. Researchers discovered how computers can understand three-dimensional scenes from camera movements alone, develop AI systems generating videos on smartphones in real time, and created medical imaging tools predicting Alzheimer's disease progression with unprecedented accuracy. This wasn't just another research day. It was a moment that could reshape visual AI forever, demonstrating capabilities that seemed impossible just months earlier. Computer vision and pattern recognition represents one of the most transformative fields in artificial intelligence today. Think of it as teaching machines to develop superhuman eyesight, combined with analytical power of thousands of experts working simultaneously. This field extends far beyond simple object recognition to sophisticated spatial reasoning. From smartphone face unlock systems operating in milliseconds to autonomous vehicles navigating complex urban environments, from healthcare diagnostics surpassing human expert accuracy to entertainment through augmented reality filters and motion capture, computer vision shapes virtually every aspect of our digital lives. The field draws from mathematics, physics, and neuroscience to solve complex visual understanding problems. Understanding computer vision requires thinking like a master chef who doesn't follow a single recipe, but seamlessly blends diverse ingredients and techniques to create something entirely new. Modern computer vision systems combine text descriptions, spatial data, temporal sequences, and visual information, using deep learning as their primary cooking method. Massive datasets serve as the ingredient supply, while unprecedented computational power provides the kitchen infrastructure. The result is AI systems that can recognize objects, understand spatial relationships, predict motion, generate realistic visual content, and reason about three-dimensional structure from two-dimensional observations. The first major theme emerging from these 17 papers centers on multimodal integration and unified control systems. The canvas-to-image framework exemplifies this trend by consolidating text prompts, spatial arrangements, pose constraints, and layout annotations into a single unified interface. Think of this like a conductor coordinating different sections of an orchestra to create harmonious symphony. This represents a significant advance over previous approaches that handled different control modalities separately, often leading to conflicts and inconsistencies. The breakthrough in compositional image generation demonstrates how multiple input signals can be orchestrated simultaneously for unprecedented creative control. The second prominent theme involves three-dimensional understanding and spatial intelligence, where researchers tackle the challenge of extracting three-dimensional information from two-dimensional visual input. This is like teaching a machine to understand the depth and structure of a sculpture by only looking at its shadow. Multiple papers address this through novel camera trajectory analysis, geometry-grounded vision models, and illumination robust reconstruction techniques. The work requires sophisticated mathematical models and robust algorithms to infer missing dimensional information, representing one of computer vision's most fundamental challenges. A third significant theme focuses on efficiency and resource optimization, addressing the critical need for deploying advanced computer vision models on resource-constrained devices. The continual error correction framework demonstrates how sophisticated AI capabilities can be maintained on low-power devices through clever architectural choices and prototype-based learning. This theme reflects practical reality. Computer vision applications must work effectively across a wide range of hardware platforms, from powerful data center servers to mobile phones and embedded systems. The goal is democratizing access to advanced vision AI by bringing supercomputer capabilities to everyday devices. The groundbreaking results from these papers present several discoveries that could significantly impact both the field and real-world applications. Camera movements alone can reveal meaningful video content without accessing actual visual pixels, a seemingly counterintuitive result that challenges assumptions about necessary information for scene understanding. The canvas-to-image framework achieves unprecedented performance in compositional image generation with multimodal controls. Medical domain researchers achieved remarkable results with glioma segmentation and grading systems, reaching 98% accuracy in tumor segmentation and 99% accuracy in classification. Video generation saw substantial improvements through the MoGAN framework, achieving increases of over 7% on established motion quality benchmarks compared to existing methods. This brings us to our paper of the day, Geometry-Grounded Vision Language Model, Unified 3D Reconstruction and Spatial Reasoning by Hugh and colleagues. This research addresses one of artificial intelligence's most fundamental challenges, creating systems that can understand three-dimensional scenes as comprehensively as humans while communicating about them in natural language. Current vision language models, despite impressive capabilities in many domains, struggle significantly with spatial understanding and reasoning tasks. They can describe what they see and answer questions about images, but ask them about three-dimensional relationships between objects or spatial layout of scenes, and their performance drops dramatically. The technical breakthrough of G-squared VLM lies in its unified architecture that balances semantic understanding capabilities of traditional vision language models with geometric reasoning capabilities required for three-dimensional tasks. The model extracts three-dimensional visual geometry features from two-dimensional inputs and uses these features to directly predict three-dimensional attributes such as depth, surface normals, and spatial relationships. One key innovation is the unified design, allowing the model to train on abundant multi-view image and video data while simultaneously leveraging benefits of three-dimensional visual priors. This approach cleverly addresses the fundamental challenge of three-dimensional annotation scarcity by learning from readily available multi-view data and video sequences. The impact and applications of G-squared VLM extend far beyond immediate technical contributions. By demonstrating that three-dimensional understanding can be effectively integrated into vision language models, the research opens new possibilities for applications requiring both semantic understanding and spatial reasoning. These include robotic systems that need to understand and manipulate objects in three-dimensional space, augmented reality applications that must accurately place virtual objects in real environments, and autonomous vehicles that must reason about three-dimensional structure of their surroundings. The model achieves comparable performance to state-of-the-art feed-forward three-dimensional reconstruction models, while delivering competitive or superior performance on spatial understanding tasks. Looking toward the future, research directions emerging from these 17 papers paint an exciting picture of what's to come in computer vision. Think of the current state as standing at the base of a mountain range, where each peak represents a different challenge yet to be conquered. The most promising direction involves continued integration of multiple modalities and development of truly unified AI systems that can seamlessly process and reason about information across different sensory channels. The advancement of efficient and scalable architectures represents another crucial direction, particularly as computer vision systems become more prevalent in edge computing and mobile applications. Today's journey through these 17 groundbreaking papers reveals a field in rapid transition, moving from narrow, specialized systems toward comprehensive, multimodal platforms that can understand and interact with the visual world in increasingly sophisticated ways. The canvas-to-image framework showed how multiple types of control can be unified into a single, intuitive interface. G-squared vision language model demonstrated how three-dimensional understanding can be seamlessly integrated with language capabilities. Medical imaging advances revealed AI systems approaching human-level performance in critical diagnostic tasks. Efficiency improvements in video generation and mobile deployment showed how advanced capabilities are becoming accessible to everyday users and applications. This analysis was synthesized using Claude's Sonnet 4 model, with TTS synthesis powered by Deepgram and image generation through OpenAI tools. Human expert review ensured accuracy and clarity throughout the process. While comprehensive analysis was conducted, some oversights may exist. All original research references are provided for verification. The goal is making cutting-edge research accessible, while maintaining scientific rigor and accuracy in representing the original author's contributions and findings. These advances represent more than technical achievements. They're stepping stones toward a future where AI systems can see, understand, and interact with our visual world as naturally and effectively as humans do, while potentially exceeding our capabilities in many domains. I encourage you to dive deeper into these papers, explore technical details that fascinate you most, and consider how these advances might impact your work or interests. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprintserver.org.